I have the pleasure and the privilege to introduce to you a group, a very famous group from Heinrich-Hertz Institute, HHI Fraunhofer, and they will present a tutorial about the latest, is it the latest, I guess, the latest video standard HEVC H.265. I think they will introduce the subject by themselves, but I just say it's Dan Grois, Benjamin Grois, Dan Grois, what? How do you spell it? Grois, okay. And Detlev Marpe is not here, but Karsten Sühring. Please welcome and start.
Hello everybody, and we are very happy to welcome all of you here in our tutorial titled HEVC Video Coding Standard, including range extensions, Scalable extensions, and Multiview extensions. Okay, so let's start. Our tutorial will be divided on 5 main parts, while the first part will focus on introduction to block-based hybrid coding. Second part, we provide some kind of brief overview of H.264 HEVC standard. We would like just to remind you several features. We will not get too deep into details because we are all actually familiar with HEVC. It was established 12 years ago. And then we will continue to HEVC version 1, followed by HEVC version 2. And at the end, we provide some kind of future perspectives and some kind of future outlook. Now, as you all know, the video compression goal is to efficiently condense the visual data, right? And to minimize the loss of the quality due to the compression. Why we need to compress the video? We would like to reduce the storage, of course, and to reduce the transmission delivery bitrate. Now, if you look at the usual HD video, the encoded rate can be some kind of 600 megabits per second. And of course, very, very high. So by using appropriate compression, we can achieve significant redundancy in the bandwidth, for example, 2%, about 2%, with some kind of sufficient visual presentation quality. At the end, we can actually decode the video stream with some kind of losses, but still acceptable. Now, nowadays, the senders are varying from some kind of video conferencing providers, security applications, which are became very popular recently, telemedicine, etc. Channels are varying from satellite channels, internet channels, storage, cable channels, and the receiver. We have a very, very heterogeneous environment with a lot of different display sizes, with different kind of devices, tablets, smartphones, etc. Now, what is important to understand then when we talk about the video coding standardization, we actually provide some kind of restriction on the bit stream, including syntax and semantics, and decoding process. This is actually what are standardized. And the rest of the things are more or less open. And by such a way, we actually permit optimizations. We allow complexity reduction for some kind of implementations. And of course, such approach provides no guarantee of quality. Now, if you look back 25 years ago, so starting, for example, from H.261, the hybrid video coding approach have been introduced. Yeah, and generally speaking, a block-based hybrid coding is first of all addressed to the scheme according to which we divide the picture to blocks. Then we apply, then we perform inter prediction, followed by transform coding. So this basic scheme is actually defines the basic block-based hybrid coding approach. This is a standard hybrid video coding scheme. We have an inter prediction here. We have a transform scaling quantization at the upper part, and followed by entropic coding. So this actually is well known. Now, when we talk about motion compensation, if we look at the current picture, we would like to find the best match, for example, in the previous picture, in order to get the minimal error. And then we get some kind of residue, and further applies the transform coding on the residue. So the residue signal should be minimal. Sometimes we just not look just at the previous picture, but we look also an additional picture, for example, picture before the previous, and we find the best match, which leads to minimal distortion, to minimal residue signal, which is then processed by applying a transform, some kind of transform. For example, the most popular, of course, is the DCT transform. And what is the purpose of the transform? Actually, we would like to convert the spatial domain pixels into transform domain coefficients. This is what we would like to do. Then we would like to apply some kind of quantization, scalar quantization mostly, for reducing a number of levels. We would like to reduce high frequencies. Okay, so actually the goal is to adjust bitrate versus fidelity. We actually decide what we would like to, which information we would like to remove, so, for example, such as movement of leaves, which is reflected by high frequencies coefficients. And of course, we decide how many irrelevant details we would like to remove. Okay, so let's briefly discuss the HEVC. I would just would like to remind you some important aspects in order to then get into HEVC, and by such a way you will be able to more clearly understand the differences. Now, when we talk about standardization, there are two main bodies, one of which is actually a video coding expert group, which was formally structured as question 6 of IEEE study group 16. The nickname VCAC originated in 1998, and its history spans from H.265 in 90s and etc. An additional organization is a moving picture expert group, MPEG, established in 1988. Its mission to develop standards for coded representation of digital audio and video and related data. Now, the timeline of H.264, it started from about 98, 99. The first model was established in August 99. The joint video team was formed in December 2001 between VCAC and MPEG's organization, which I mentioned a minute ago. The chairs have been Gary Sullivan, Ajay Luthra, and Thomas Weigand. And a couple of years later, in May 2003, H.264 have been approved as a recommendation, H.264, yeah, and then the work started on the extensions. As you know, FREX extension, latest Scalable extension, Multiview extensions. This is generally common profiles of H.264. The most popular are baseline, of course. We have main, we have high profile. We have quite many different options. This structure, by the way, is called onion-like structure. So if you look, for example, at several profiles, they contain like main profile, like main profiles, they contain already some features of the baseline profile and extended profiles. It's not completely onion because the main doesn't contain all features of baseline, but anyway, it's onion-like structure. So, as a summary, HEVC generally is based on hybrid video coding approach, similar to other standard, to its predecessors, with several improvements. The key improvements are enhanced motion compensation, small blocks for transform coding, the blocking filter, of course, some kind of enhancement to entropic coding. We will get a little more into details now. And of course, it achieves a significant bitrate savings of about 50% compared to its predecessor, MPEG-2, for the same perceptual quality, of course. Now, generally, according to HEVC, the picture is can be partitioned into slices. Slices are self-contained, and they're actually a sequence of macro blocks. A macro box contains 16 or 16 luma samples and 2 of 8 on 8 chroma samples, of course, which can be further partitioning for prediction purposes, etc. This is a general basic coding structure of H.264 HEVC. It's well known, so we have inside the encoder, we have a decoder loop, we have an inter-prediction, we have a deblocking filter, which is also provided quite good enhancement for the quality, and we have a transform quantization scaling, and finally we have entropic coding at the end. Now, common elements for previous standards. First of all, we talk about macro blocks, 16 on 16 luma plus 2 on 8 on 8 chroma samples, block motion displacement, variable block size motion, block transforms, scalar quantization, which also was inherited from previous standards, and usage of IP and B coding types. Now, let's just a little get into refresh your memory into more details. We have, in order to perform a prediction, we actually can divide macro block to regions, not too many. In HEVC, of course, we have much more options. So the macro blocks are divided in such regions for in order to improve coding efficiency. Motion vector accuracy is actually quadruple with 6-step filter. An additional important feature is the usage of multiple reference frames and generalized B-frames, as well as weighted prediction, which also was introduced in HEVC. When we talk about multiple reference frame, of course, we can get a reference not just from the previous picture, but from other pictures, and by such a way we can reduce a residual signal and encode the video signal in a more efficient manner with less bits, of course. And by such a way we can jointly exploit sync cuts, aliasing, some kind of uncovered background, and other effects. Okay? And of course, in case of bidirectional pictures, we decode 2 sets of motion parameters because of a bidirectional issue. As we know from MPEG 2, MPEG 1, this is a known dependencies. So the new dependencies actually are illustrated here. It allows to decouple the reference order and display order. Yeah, you see here the line. What else? An additional issue is the interprediction improvement. We have a directional modes. Only 9, yeah, not too many, but it's also provided quite good results compared to MPEG 2. Regarding the transform coding, we have relatively small block integer transform sizes of 4 and 4, also repeated transform of DC coefficients, which provided quite good performance. And regarding the entropic coding, which is actually the last stream of encoding, is CAVLAG, content adaptive variable length coding, which is based on X-golem code for all symbols except for transform coefficients. The coefficients are actually scanned backwards. It's also important in order to improve the coding efficiency. An additional scheme which is actually performed better than variable length coding is a content-based adaptive binary arithmetic coding, which is also used in HEVC. According to KABAK, we use adaptive probability models for most of the symbols. We exploit symbols correlation by context, and by such a way, actually, we can get quite fast binary arithmetic coding, which is based on lookups and shifts only. Okay, so this is more or less a brief overview of HEVC. I suppose that you are all familiar with it, so I'm not getting too much into details. Just to refresh your memory, as I said, and now we are getting to HEVC version 1. This is, by the way, known test sequence, picture from the known test sequence, kimono. Now, let's talk about the motivation for HEVC. As you all know, currently HD already not big issue. I remember, let's say, 5 years ago, it was like considered to be state of the art, but nowadays we are all talking about 4K resolution, 8K resolution, and even more, 16K resolution. Most of us has already HD displays in our homes, laptops, etc. And mobile service is also going toward HD. Stereo multiview in 3D also emerging, and resolution are continuously increasing. So I cannot predict what will be, for example, in 5 years, but I suppose that 4K will be in the same position as HD today. So we will all, most probably will have at our homes television with 4K or maybe even 8K resolution, I don't know. My personal, let's say, so dream is to have a home with walls as displays. So with HK displays, by such a way I can press a button and get into the environment that I want, So I suppose it will be the future, maybe 20 years from now, when the actually cost of displays will be much cheaper than the cost of building blocks. Okay, so video actually has, as I said, multiple dimensions to increase the data rate. We have increase of spatial resolution, temporal resolution, frame rates, We have an increase in color gamut space. We have an increase in bit depth, multiview, 3D, etc. According to the recent forecast of Cisco, by the way, every year issues quite detailed report of forecasting to the next 5 years, like what will be the consumer internet traffic, video traffic, etc. The report are quite extensive, so if you have time, take a look at it. So according to this report, which was issued this year, the consumer internet traffic will be around 80% of all consumer traffic by 2090, which is a lot. Not including peer-to-peer and file sharing. And according to this forecast, sum of all forms of video will be in the range of 80–90% of the global consumer traffic, which is really, really a lot. Today, we have different types of content. So those of you who have actually dogs can enjoy, I don't know how it's in Germany, but several countries they have kind of dog TV. I also get exposed to this TV. It's quite nice. They have quite relaxing scenes with animals running, with dogs. So to attract the dogs to the TV screen if you don't want the dog to be going around when you are outside the house. And also in San Diego, for example, they have a Catbox TV channel, so your cats can also enjoy TV in their free time. And of course, in order to enable so high quality video services with so huge plurality of new content, especially for 4K and 8K resolution, we need efficient compression techniques. So when actually HEVC was developed, 4K and 8K resolutions have been quite intensively considered. So it was especially designed for high resolution videos. The applications, the field of applications which can be used for HEVC based schemes is really, really large. It's including internet streaming, real-time conversation services, home digital cinema, content production distribution, medical imaging, which became more popular recently, storage media, surveillance application, drones. Yeah, nowadays drones use already, many of the drones use cameras, so it's also quite, it'll be quite nice to have some kind of good resolution and long videos. If we allow to compress efficiently the data, we can actually store really long video, yes, and wireless displays. So, in 2010, both organizations, VCAC and MPEC, established a joint collaboration team, which is called GCTVC, and issued a call of proposals. So it was about 5 years ago. And as a result, after 2.5 years of extensive intensive development, the high efficiency video coding have been approved. For the call of proposals, there was submitted 27 complete proposals. Every proposal that have been submitted contained a lot of encoded video documentation, so the work that have been invested is really, really huge. Yeah? There was a lot of efforts from many companies in order to analyze, understand the technology, etc. So this 2.5 years was really, really intensive. Benjamin Grois is actually a co-editor of HEVC, so he knows better than me how much work it involved. Already from the beginning, some proposals, according to some proposals, the comparable quality was achieved in half of a bit rate. Now, all proposals basically was conceptually similar to H.264. So actually, it's also, the proposals have been based on hybrid video coding. It included block-based with variable block sizes, block motions, spatial interrupt prediction, spatial transform. So quite many features remain the same, and except for several, which I will overview now. But the basic approach, the hybrid-based approach, has remained the same. By such a way, actually, it allowed the companies to make more smooth move towards the new video coding standard. Yeah, generally, we don't want to make so-called a revolution unless it's really like we really get significant results. Yeah, because we would like to allow the industry to get smoothly moved towards the new video coding standards based on the already existing platforms. If we look at the meetings timeline, as I said, it started 2010 in the Dresden meetings, and it was approved in January 2013 in Geneva meetings. And the aligned text specification was actually announced as a recommendation H.264 by ITUT and by ISO as MPEG H part 2. So when you actually hear MPEG H part 2, it's the same, but it's like a nickname of ISO organization. Now, what is important to note that from the high-level point of view, from the high-level design, it's similar to HEVC. The network abstraction layer is actually packet-oriented, based on packet-oriented payload. We have a null payload types. The pictures are also structured into slices, and as I showed before for HEVC. However, it includes additional features, such as tiles and wavefront for better parallelization. Karsten and Sühring now will explain in more details. If we talk about video coding layer, so as I said, it's based on hybrid video coding, and the main scheme or the hybrid video coding scheme is actually more or less the same. Okay, so Karsten and Sühring will now provide more details about the high-level syntax of HEVC.
So, before we go into the actual details of the coding tools, I want to give you an overview of what's in there in terms of infrastructure. So high-level syntax basically is all the gluing code, the syntax around those coding tools. You need it to access the actual packets, so you can packet by packet, parse, bitstream, and of course you need to transmit the settings of the tools that you use for coding, and you need random access information, so how to tune into a bitstream, and of course you want to transmit metadata as well. So basically when it comes to high-level syntax, there's very few types of syntax elements used for coding. You have fixed length elements here. There are 3 different types. One is a type for predefined values. The second one is one with a fixed length that's known upfront. The third one is which is one that's dependent on other values. And the last one is an X-column code, a variable length code. And those variable length codes are designed in a way that they increase their length with the value. So very low values are very efficiently coded, while higher values are getting less efficient because you have to transmit the size of the syntax element in that X-column code. So if you know upfront that you usually code very low values, then these X-column codes are quite efficient. Otherwise, if you have a random distribution and you know how many bits you need to spend for a value, fixed length codes are more efficient. But yeah, it's basically to keep everything very simple in high-level syntax. That's just the types that we're using here. No cover coding, just those simple codings. In general, if you want to access a bitstream, you can put HEVC into different packetization formats. You can use MPEG-2 transport stream, you can use RTP packets, you can use a file format. The most simple version that's also defined in standard is the NXP byte stream, which was also there in H.264. And basically you put the video into a file where you have a start code at the beginning, which is just a specific type of codes here, which is 2 0 bytes and a 1 byte, or 3 0 bytes and a 1 byte. And then you have a header there, and then the actual payload for the null unit. So the null unit is a very basic unit that you can access in bitstream. So let's look at these null units. They're quite similar as in H.264. The basic idea is to have a packet that can be transmitted over a network. And what we did here is to increase the size of the null unit header and make it another byte long. So it's 2 byte now instead of 1 byte, but that really helps us, especially for the extensions in version 2 that we're discussing also today, because yeah, we were really looking, when we designed the first version, we really knew that we will have multiple layers there in the really near future. And with H.264, we had to work around the issue there that we couldn't select easily layers. Yeah, then in the payload, we make sure that we don't have these start codes appearing there that we have used to distinguish the packets. So let's take a closer look at the null unit header. Basically, we have 4 syntax elements there, and all have really fixed lengths, so that a network element can easily look into these packets and figure out if we want to select a specific layer or a temporal sublayer. We can just look at some bit field and read the value there and take it out, or decide whether we want to transmit a packet or not. And so the very first bit is a forbidden bit that's there, basically to avoid conflicts with MPEG-2 transport stream headers. Some applications also use it for signaling that they detected the corruption in the null unit. Then we have a null unit type, which says which kind of packet that really is, whether it's metadata, it's a video coding layer packet. Then we have the layer ID. In version 1, we only support 1 layer, but with the extensions Scalable, Multiview, we allow that to be non-zero, so we really have multiple layers there. And then we have also support for temporal scalability already in the first version, and that's why we have a temporal ID there, which shows the temporal layer. So the null unit payload, we have basically 2 types. One is VCL payload, which is actually the slice segments that have decoded video data, and the other type is the non-VCL payload. That's all the metadata around it, the parameter sets, SEIs, and access unit delimiter, end of sequence, filler data. We'll have a look at these on the following slides. So in general, I had an overview here. Let me go back. Yeah, we have access units. Basically, the concept of an access unit is that it contains a complete picture. If it's a multi-layer representation, we also have all layers in one access unit. But an access unit can be can consist of several null units. So you will, in the middle of an access unit, you will, in any case, have coded slice segments, which are carrying the image data. They can be preceded in the beginning with the access unit delimiter, which is just there to distinguish the access units. You can have SEI messages, you can have parameter sets in the access unit, and in the end, you can also have end of sequence or end of bit stream markers. So parameter sets are already known from H.264. We had a sequence in the picture parameter set there. What's new now is the video parameter set, and that's supposed to describe the general overview of the whole video bit stream. So there's also the idea there that you want to have an overview of all the layers that are included in a bit stream, which is not so important if you have a single layer bit stream in version 1. But it's really, we mandated it to be there also in version 1, that a version 1 decoder can later figure out, okay, that's a multi-layer bit stream, but there's a base layer in there that I can decode, and it can pass the information from the video parameter set. But mostly in version 1, there's a duplication of the information in the sequence parameter set. Yeah, here's a list of things that are in there in the version 1 video parameter set. The number of layers, which is of course in version 1 just 1 layer. The description of the temporal sublayers, profile tier level. So that's important if a decoder tries to figure out whether it can decode a bit stream or not. then it can look at the video parameter set and see for every layer and also all the temporal sublayers these constraints and figure out whether it has a capability to decode. Timing is in there, optional HRD parameters. And then in version 2, we get the actual description of the layers. So we know which layer is scalable, what is multiview. In version 3, we will have also depth layers. We allow auxiliary pictures there. Then we have a description of the dependency between the layers. And there's a difference between output layer sets and the layers that you have to decode. So you can specify to decode like 3 or 4 layers, but just to output 2 of them. Representation format describes the picture size, the spatial dimensions, and the chroma type, and the bit depths. And there's also WUI information like we know it from the SPS in H.264. But that was the scope of the complete bit stream. Here's the list of the stuff that's in the SPS. That's quite similar to H.264, except that we now have specific settings here for the tools that are in HEVC. But in general, that's the SPS has the scope of one layer, a sequence in one layer. So for each layer you would use a different SPS. So I give you a second to read. I don't have to read everything. In version 2 we have extensions there for range extensions, the switches for the tools. For multi-layer there's a very simple constraint flag in there. Then the picture parameter set also has switches for a lot of tools in there. Picture parameter set has a scope of a picture, so it can be changed for every picture, but usual encoders wouldn't switch it for every picture, so a picture parameter set is usually shared for several pictures, but it could be switched in every picture. Activation of parameter sets work the following way. In the beginning there's no parameter set active, and then when we encounter the first picture, which is usually a random access point, then we activate those parameter sets along their dependency chain. Basically in the slides we have a pointer to the picture parameter set. The picture parameter set has a dependency on a sequence parameter set, and that to the video parameter set. And we can repeat these parameter sets as we wish for error resilience, or we can transmit them earlier. I show some examples here. That's the most simple example. We just put the parameter sets in really at the beginning of the sequence or of the bit stream, and then when we have a random access picture, we reference them. Alternatively, we can put before every random access point, we can just put a copy, so that we can really go into the bit stream at the random access point and don't need any advanced knowledge of the parameter sets. So that's more suitable for random access here. Third version would be to transmit a new parameter set somewhere in the middle. So we would share the video parameter set here and have an initial set of parameter sets that we use at the beginning of the sequence. At some point we decide we need to change the parameters, and then we can just transmit new parameter sets and activate them at the next random access point. Another way what an application could decide to do is to transmit all the parameter sets in the beginning with all different variants that it intends to use later. For instance, it could also be hard-coded in a receiver box, for instance, and then the random access points will just refer to these pre-stored parameter sets. So that's also still a valid option to do. Now I want to go on to random access pictures and how to use them. The new thing there is that we have CIA pictures and BLA pictures. The IDR picture is already known from H.264, but the CIA is a new picture type that allows an open GOP type of access structure, so that we can have a more consistent bit stream there. I'll show some examples on the following slides. And we have support for temporal scalability, and we need some access pictures for that type as well. So let's start with the IRAP pictures here. I said that's the IDR picture that we have that's well known. Then we have the clean random access picture, and the broken link access picture is one which is basically a CIA picture, which indicates that we have random access at this point. All these types are intra-coded, so that we don't need any reference pictures. We can just start decoding with that picture. The nice thing about the CIA picture is that it is less constraining than an IDR picture. So we can use more references on pictures that are following in decoding order after the CIA picture. We can have pictures that are not decodable if we do random access in the CIA picture. And that's why we have two more picture types, which are Razzle and Rattle. So I'll continue with those later. But the GOP types that we can do with CIA pictures are really allowing us to improve the visual continuity. So usually what happens in an IRAP picture is that the encoder completely starts new coding independently completely of everything that happened before. And then if your quality is not, if you see some artifacts, usually you see a change in artifacts there, and that might be visible like an intra-pumping that you might have seen in coded video already. So I think I said everything about BLA already. It's basically a CIA picture. Maybe that's getting clearer when I come to the examples in the next slides. So that's a very simple example here. What we did in H.264, we had the IDR picture in the beginning, which is really the first picture when we start decoding. And now with the open GOP CIA pictures, the following random access points, I would usually use CIA pictures because I can use these CIA pictures, the IRAP here and the CIA as dependency for the pictures that I code after the CIA. Let's skip those slides here for the moment and go directly into the example. That's a typical IRAP GOP. So we now have these hierarchical coding structures here. I have an I picture at the beginning. I would have coded next a B picture here, and then I go to a B picture here in the middle, and then I go further up here, and then I would code those with these dependencies here. I don't know how much you have been working with these types of GOPs already. But that came very usual in H.264 coding because it provides a really good quality. You can just code these pictures with less bitrate because they are very close, have very close relationships to the neighboring pictures. And if you put a really good quality on these base pictures, that helps you in overall quality. But what you have if you need a new random access point, then you would put an IDR picture here, the next on the highest layer, and what you get is a prediction boundary here, where you cannot use any cross predictions there, and this whole structure here gets unbalanced. You only have dependency on this side, and you don't have any dependency on this side. So there you have the visual border where the artifacts would change. You can try to counterbalance it and put the IDR picture right next here, so you have a more balanced GOPS here, but what remains still is this border here. With the CRA now, this border basically disappears. So you can have, you would code after the first GOP, you go ahead, code the CRA picture, and then you code all these B pictures here that are dependent on it. But if you start decoding at the CRA picture, you obviously don't have that B picture here. So you cannot decode all these dependent pictures here, and that's why we have this Russell type random access skip leading pictures. Those describe pictures that are not decodable if you do random access at the CIA picture. Then one thing that we have now is clear support for temporal scalability. There was support for temporal scalability in H.264 in the first version as well, but it got improved in the Scalable extension. But now we have it really from the beginning in version 1 here. We can have assigned temporal sublayers to a picture, and if you assign a picture to a higher temporal sublayer, it may not may only access pictures at the same temporal layer or at lower layers, so that you can just remove higher temporal layers and don't lose any reference pictures that you need. And if you want to access temporal sublayers, you can always do that at random access points. You can switch up to decoding the whole bit stream with all temporal layers if you go to a random access point. But sometimes that's an interruption in quality. If you put an IRA picture in there every time when you want to switch up, that may not be desirable. So that's why we have temporal sublayer access pictures. And at the TSA picture, you can basically switch from the layer below to the layer of the TSA or any higher layer, which I'm illustrating here. So this is typical in the beginning of the IDR picture, and then I have a TSA picture here where I have no dependency on the same layer, and also all other higher layers don't have a dependency within that layer. So I can, at this point, I can decide also to go to sublayer 2. Here, obviously, I don't have any higher layers, so I can also put a TSA picture in here. But if I decide I want to have a TSA picture here, I have to break this dependency here. I can only have a dependency on the lower layers. Another variant of that is the stepwise temporal sublayer access picture, and that allows just accessing the next higher layer. So here in the beginning, those are still the TSA pictures, but here at this point I can only switch to sublayer 1 if I'm decoding sublayer 0 so far. But if I would switch to the second layer, I would be missing the reference picture here. So the stepwise just allows me to switch this one layer up. If I want to make this a TSA picture, then I would just have to break this dependency here. So another new thing is the reference picture sets. In H.264, the decoded picture buffer was operating on state. So basically, in every picture, you had an indicator whether the picture is a reference picture or not. And if you had a reference picture, you would put it into the decoded picture buffer. And then you could use memory management control operations to remove pictures from there. But you never had a complete description of the buffer state. And that's a new thing in HEVC. Every picture comes with a reference picture set or a reference to a reference picture set, and so you don't depend on that state anymore. You have an explicit list of the pictures that are supposed to be in the decoded picture buffer, and at this point you can easily detect if a picture is missing, if you have lost something, and you see that picture in the list, then you know something went wrong, and you can do concealment there. And in H.264, that was kind of guessing if something is missing or not. Only if you saw a reference to the picture, then at the video coding layer, you would really see that there was a loss. And signaling here, you have short-term reference picture set that can be stored as a template in a sequence parameter set. So if you have a regular GOP, you would put all the templates that you need for each picture into the SPS and then just reference it. And the more complicated thing is the long-term pictures. We also have still support for long-term pictures, but that long-term picture needs to be transmitted in every picture as well, the reference to it. So the long-term picture, the state there was quite a nice thing to have in H.264, but really there you still couldn't detect if something got lost, if you were missing that long-term reference picture. Then you would really notice it very late in the coding process. Those reference pictures that can be transmitted really efficiently. There's a prediction between them possible, but I won't go into the details of that. Reference picture list modification that allows us to switch the order of the reference pictures or select other pictures than the default lists. That has also been simplified compared to H.264 because we were expecting very complex lists, so we had a sophisticated mechanism to create these lists in H.264, and in HEVC we just signal the POCs of the POC differences of the reference pictures, and we have quite explicit list here as well. SEI and WUI are concepts that we also know from H.264. That's quite similar. That's all metadata. WUI is in the sequence parameter set. SEI are own null units. You would use them for buffering and timing information. There's frame packing as an indicator where you would say if you put multiple views into one coded picture, then the decoder can figure that out and split that into different views again. Display orientation is one thing. Interlace is also now just a metadata field. We have no interlace tools in the coding layer. And in WUI we have HID, clock parameters, color space descriptions, aspect ratio, and constraints. So the second part of my section of the tutorial here is the parallel picture processing. When HEVC was developed, people knew already that this thing is going to be much more complex than H.264, and especially at the encoder side. So they were really looking into polarization concepts. And slices are already known from H.264. What's new is tiles and wavefronts. All of them are areas of the picture that can be decoded independently. And one thing, that they're not completely independent because it's possible to filter across the boundaries so that you don't get any visible edges. But in general, the main decoding process is independent. So let's have a look at slices first. This is a picture here, and I've used different colors to indicate different slices. What's new is that we have dependent slice segments now. Basically, if in the beginning I would signal a complete slice header, and then at some point I can say, okay, I go into a new null unit and just signal a very short slice header. And that would be a dependent slice because I'm just inheriting all the slice information that I've transmitted in the first slice segment here. And we now use the term slice for one independent slice segment plus all the dependent slice segments that belong to it. So it's in terms of language, it's a bit different now. A slice was completely one null unit in H.264, but now a slice can be multiple null units consisting of one independent slice segment and 0 or more dependent slice segments. And that's all in raster scan order. So you don't have any reordering here like FMO or like tiles will do it. Some property of slices, each slice can have a different picture type. Unless you're in an IDR picture where you have to do intra all the time, but you can basically switch inside the picture between IP and B. You can have different reference picture lists, you can have different filter parameters. And here's some usage scenarios. One thing is if you have a MTU size where you want to have your network packet adapted to it, then you can stop inside the picture and start a new null unit with a new slice segment. If you want to do a low delay operation with wavefronts, then you can use dependent slice segments. And for error experience, if you want, if there's a chance to lose a packet, then your smaller packets may help to just lose a region of the image, not the whole image. Parallel encoding and decoding of these slices is also possible. Another tool for parallelization is tiles. What we did here is to split the picture in rectangular areas, and those rectangular areas are independent of each other. You have raster scan order inside the tile, but then if you are finished with the first tile, the next CTU starts here in the second tile, the third tile, and the fourth tile, and so on. And these patterns, how to split the tiles, can change from picture to picture, but usually encoder would keep that steady. But basically, if tile boundaries get visible, it could be switched over in different pictures. Each slice, each tile can consist of multiple slices. I've tried to put different shades in here. I don't know if that's probably visible there from down there. But a slice, so either there are constraints on how tiles and slices can be mixed with each other. So basically, if you have multiple slices, then all these slices cannot span the tile boundary, and the other way around. You can have one slice for everything, but multiple tiles inside that slice. But mixing in between is forbidden. And you can still filter across the tile boundaries so that those don't get visible too much. Another parallelization tool is wavefront processing. It has been done in H.264 as well, but now we have real support here. Basically, what you do is you process the first line, and then when you have processed the second CTU, you can start processing the second line, and when you are there at the second one, you can start with the third one. So you put every line into an own thread, and with delay, you basically get a pattern that's moving like that wavefront through the picture. That's where the name comes from. And what allows that is that we don't have to wait for the last block for the Kabak dependency, because Kabak uses the context usually from the last coded CTU, and we do inherit the context state from the second CTU here, so we don't have to wait for the decoding of the final block in that line. Basically, the problem for the decoder is how to find the position in the bit stream of that where the second thread needs to start. There's a mechanism called access point, which is an offset pointer into the bit stream. But if an encoder wants to write out these information is really fast. Basically, it would have to wait till the encoding process of the whole picture is finished to find these access points. What we can do is to use dependent slice segments. So I would put every line in a different slice, and I don't have to use this access point mechanism anymore because I have a new null unit for each line. And with the dependent slices, there's not too much overhead. Here's an overview of the coding performance of different tile patterns. At the bottom we see the different patterns in rows and columns. So that would be 2 columns in 1 row, so there's very minor performance impact. If you really use a high subdivision in one direction, then you will obviously have a higher impact on coding performance because you prohibit the inheritance of parameters at the tile boundaries. So yeah, basically the more tiles you use, the more loss you will have, which is obvious, but also patterns that are really dividing in one direction and not equally splitting are also hurting performance quite a bit. And my last slide is this overview, which tries to compare the different polarization approaches. So in slices we have quite a high loss. This gets much lower with wavefronts. You have boundary artifacts in slices and tiles, which is also not there in wavefronts. Single core issues means if there's an impact on decoding just with one core, if you don't want to do polarization in the decoder, is there any effect on the decoder? And that's not the case for slices, no, not really. But for tiles you have to change the scan order. So especially hardware people are really see that as a problem. Yeah, polarization, there are usually a lot more parallel processes possible in wavefront coding because every line can be used in a different process, and you would use a different slice or different tile. You would need different slice for a new thread. And yeah, region of interest coding is possible with tiles, but not with the others. So I think that would be a good point. If you have any questions for the whole high level and polarization part, please ask now. Otherwise, we'll continue with the low level tools.
What is the speed up?
Well, basically, if it's independent, it's a number of threads. With wavefronts, obviously, you have some delay and some overhead for synchronization. So yeah, you can't say for tiles it's factor 4 because you still have to do the filtering, but it's getting close to that. If you have 4 tiles, then yeah, maybe around 3.5. I don't have concrete numbers here.
Okay.